Hi everyone. Back when we talked about quantum field theory, I mentioned the fact that every fundamental particle falls into one of two categories. It's either a boson, which will transmit force, like the photon is an example of a transmitter of the electromagnetic force, or it's a fermion, which is the things that do the exchanging. There are also exclusive, and I mentioned the fact that they make up the foundation of matter, the things that we think about as being, hard, solid type objects, the stuff of the world. And now we're in a position to understand that a little bit better, because what we're talking about in this slide is something called the Pauli exclusion principle. The Pauli exclusion principle says that no two electrons in an atom can possess the same four quantum numbers. And what I mean by that is, take as an example helium. Helium has got two electrons. Take the first electron, it's going to sit in the lowest energy state available to it, which is principal quantum number of n equal 1, and you're done. So that's good. Take a second electron, and it's going to seek its lowest energy level also. It wants to go in that n equal 1 slot, and it can, because the two electrons can have different intrinsic spins, so one up, one down. So that doesn't violate Pauli exclusion principle either. They have the same n value, they have the same L value, they have the same M value, 1, 0, 0, respectively, and they have different spin. Now, a third electron comes along. Say we're talking about lithium. Lithium has 3 electrons, and so the first two do the same thing that they would in helium. The third electron cannot get into that n equal 1 energy state. So it has no choice. It has to sit in the energetically less favorable n equal 2 quantum number. So that means that that electron is pretty easy to strip away. It's much easier than it would be from helium, for example. That's what we call the ionization energy. So the ionization energy of lithium is much smaller than helium. Now, let's move down the periodic chart a little bit, and the next one is sodium. Sodium has 11 electrons, and you kind of go through the same type of pattern. The first 2 fall in that inner shell, like normal. The next 8 fill the n equal 2 shell. And the reason for that is, in every spherical harmonic pattern, you can always get 2 electrons, back to back like this, up, down. So really, in that n equal 2 energy state, there are 4 possible patterns. And that is how things progress, that it goes n squared, the number of possible ways or number of possible patterns. And so, it's 2 times n squared is the number of electrons that can sit there. But the point is that these 8 electrons fill that n equal 2 shell. So the 11th electron, you've got 2 in the center, 8 next. So you got 1 left. That 1 left has to sit in n equal 2, n equal 3 principal quantum number. Which is why sodium acts like lithium, because the chemistry associated with these atoms is completely dominated and controlled by the shape of these electron orbitals. And so lithium and sodium are going to act the same. Now, the same thing happens on the other side of the periodic chart. Let's talk about fluorine and chlorine. Fluorine has got 9 electrons, so it's got 2 in the center, 7 on the outside. It's got a little hole, right? Because 8 will fill that outer shell. So it's got a little hole, which means fluorine is very willing to accept electrons. It wants another electron to be complete, right? And so it has a propensity to do this. So chlorine does the same kind of thing. chlorine has got 17 electrons, and so it's got 2 in the center. It's got 8 on the outside. That's 10. And so we've got 7. 7 are sitting next in, and basically we want to get 8 in that next shell. And so the chlorine is also very accepting. And so that's how sodium chloride works. Sodium's got an extra electron. Chlorine wants another electron. They get together and basically exchange that extra electron, and they're both happy, but now one's positively charged, the other's negatively charged, and so they attract one another through electrostatic attraction. That's an ionic bond. And we could go on and on talking about how the principal quantum number, the angular quantum number, and really create the periodic chart as we know it.